This video is about burning fuses, any fuse configuration to devices from the AVR range. Specifically, this is a video as part of the series of videos we're doing about making custom circuits with your own microcontrollers and Arduino. So we're going to be looking at the ATmega328P, and we're going to be doing the burning of fuses using an ISP programmer, specifically an Arduino As ISP, as that is a homemade programmer, so it's easy to get one. In order for this to be useful for other people that might come here with the idea of generically how do I burn fuses, what are good tools to do it as of now, which is December 2022, we're going to organize this video so that it's also helpful for those. So we're going to start by talking about what are the tools and how do you use it. And then we're going to talk about potential fuse configurations that you might make, which can cause you problems that might even end up, well, your microcontroller might not be usable anymore if you do certain things in certain ways. And at the end, we're then going to go into specifically the two fuse configurations for the ATmega328P, which you cannot do with the Arduino IDE and the miniCore because they're not implemented in the miniCore, so they're not there in the tools menu. However, you can do them here, and they are useful in some situations. They are useful. They're not quite as common as the rest, but they can be useful. Now, the tools. The main tool we're going to be using is AVR Dude. AVR Dude is a command line tool. It's not all of this, it's just a command line tool. And it supports quite a large number of microcontrollers because it supports pretty much anything from the AVR range. And that's a huge range, and not everything is just programmed with ISP. There's quite a lot of different ways of programming them. Some of them, the older ones, do support ISP, but the newer ones support things like UPDI, for example. So it also supports quite a large number of programmers. Now, what that means is that as a command line tool, it's going to have a lot of parameters, command line parameters. And some parameters will make sense with some microcontrollers or some programmers, and others won't. That means that coming in and trying to do something with this, if you've never done it before, anything, it's going to be a nightmare. Because, well, even the manuals for this thing aren't all that good. And then part of the configuration depends on configuration files. So part of the parameters depend on the configuration files you have. So it gets really messy. Hence, we have here AVR DoDes. And AVR DoDes adds on top of AVR Dude this nice user interface, which is still a little complicated when you just arrive here and see this. But it's actually a lot simpler than, well, command line parameters. And AVR DoDes just calls AVR Dude with the right parameters. And it enforces certain things so that we cannot do things without having specified everything that it's specifying. So if I don't select a microcontroller unit here, I can't do anything on fuses or with the flash memory or with the EEPROM memory. Because, yeah, it doesn't make sense, so it doesn't let you. And when it does let you do things, then it passes all the necessary parameters, not just a few or whatever. It doesn't make the mistakes a person would do if you just arrive here and you're trying to figure out what to do and you forget something. And you didn't even know you needed to pass it, right? This thing will know for you. So that's the whole point. So, how do you get them? Well, if you're using the Arduino IDE with a miniCore, you have AVR Dude in there because the miniCore uses AVR Dude to upload programs to the microcontroller chips and to burn fuses, also burn bootloader. So it's there already. If you don't, you'll have to go and download it and install it. And I mean, we're going to explain this so that you don't need to worry about is it a newer one with new configuration files or an older one or whatever. So just get one and install it, right? But ideally, the one that comes with the miniCore is properly configured to do what we're going to do here, because yeah, that's the whole point. AVR do this. Yeah, Google it and install it. I mean, that part is even easier than using it, and using it is a lot easier than AVR do it. So, how do we use it? Well, the first thing you need to configure is the programmer. Without this configured, nothing else works. So, say we're going to use the Arduino As ISP programmer. So, how do we do it? Well, here there is an Arduino ISP programmer. It doesn't work. Or maybe it might work if you have newer configuration files. I don't know. Yeah, that's part of the problem. Other programmers, not as much as a problem here, but this one for sure. Well, or maybe not. That's exactly it. Depends. So what does not depend and always works? Well, this one always works. Why does it always work? Well, this is a very, very old programmer. And from the days Atmel was still called Atmel and hadn't been bought by Microchip. So this programmer is supported from the very beginning in AVR do it. So that's always going to be there. And guess what? The Arduino As ISP application, which you upload into a Arduino Uno, Nano or Mega board to make it a homemade programmer, implements the protocol from this one. So it talks the same, basically. It expects the same commands, it replies with the same, with the correct answers, the same kind of answers. So AVR do it, when talking to this can just as well be talking to an Arduino As ISP. So that's what we're doing here. We're just choosing this for the protocol. So, what else do we need to do? Well, it's a serial protocol, so you need to give it the COM port. There you go, in this case, COM7. Of the Arduino As ISP programmer we have. We also need to do something we don't need to do in the Arduino IDE with the miniCore, which is we need to give it a baud rate. Why do we need it here? Well, here you have full freedom, so yeah, you need to give it the baud rate. This is the default. So this is the same that if you get your Arduino As ISP application to make the homemade programmer, there's going to be the original one. It's going to be serial.begin in there with this baud rate. And guess what? I mentioned the original one. Why? Well, you can hack it, right? You can go there and change that. And then you can come here and you change this. And guess what? It works, right? So you can make things go faster. You cannot make things go faster with the Arduino IDE miniCore because that one has this hard-coded. That's why you don't have to tell it there, because it's already there, but you can change it, right? Here you can do whatever you want. So yeah, if you are doing stuff that moves lots of data out into a memory or out of it, like, I don't know, read logs from the EEPROM or write pre-compiled applications to a series of microcontroller chips, it might be worth it to increase the baud rate here and in your homemade programmer, if you will hack it to go faster, and this thing will go faster along with it. So yeah, problem solved. So there you go. This is done. What do we do now? Well, we can do something here we cannot do in the Arduino IDE. We can just detect what's in there. And this tells us two things, right? The first thing is, yeah, the programmer is in there, and yeah, this does work with it, and it's properly configured. And the second thing is, well, that's an ISP programmer, so it's connected via the ISP pins, so reset and SPI pins, to this microcontroller. So that's what's in there, which is kind of what you would expect it, right? So now we know that this is there. So what next? Well, we'll do something that you cannot do in the Arduino IDE. Also, we're going to read the current fuse configuration of that microcontroller and look at the numbers here whilst we read it. You can see it changed. So these are the actual values from the microcontroller. And you can see here why we would rather use AVR IDE than do this by hand, because it gets complicated, right? So yeah. What do we do with the numbers here, right? They're numbers. So what do I mean? Well, this is the other tool we have to use. This is the non-line AVR fuse calculator. There are various ones, and there are some offline also. I like this one. Everything comes up in just the one screen and it works nicely, so we're going to go with this one. Notice there's also here the big fat list of microcontrollers, just like AVR IDE and AVR IDE. It's here also. I've pre-selected one we're using. So, okay, how do we use this tool with the rest? Okay, L here, I'm going to copy and paste the numbers. L stands for low. Notice here, this is a low fuse. Notice this has changed. Notice here it also has changed. Same thing with this one. H stands for high. And E stands for extended, which I'm not going to copy and paste because it's already there, FF. So, now what we have here is this has the current configuration of that microcontroller. And the first thing you might notice is that the default and the values we have is the same. That's because the microcontroller is configured with a factory default. Hence, the default's here also. The next thing you might notice, if you know binary, is that FF is not at all, well, doesn't look like this at all. What's going on? Right? This is supposed to be 0, not FF. FF is all ones. Well, there is this special characteristic with fuses, well, the documentation about fuses, if you will, which is, well, fuses, flash, EEPROM, all those kinds of memories are programmed in a slightly strange way. You don't set there the byte you want it to have. You first erase it, and the erasing transforms it all into ones. All bits become 1, and this is to do with the actual physical characteristics of the memory. And then you write the zeros. You burn the zeros. You erase to get ones, and then you just burn the bits that are 0. Or program, if you will. And yeah, here you can see a reminder for that. The flags you see here is for the fuses which are to be programmed. So they're the zeros. Hence there's nothing here because the final value that's going to be in that memory is going to be FF. It gets erased, so everything becomes 1, so you don't have to program anything. But in this case, it's different because in order to achieve this, is first erase everything and then you program just these 3 zeros, nothing else. So, but if you notice, I'm going to give you here an example. You can see divide clock by 8 internally and clock diff, and it's a 0. Yet here it's checked. So it goes back. So here this thing is actually, if you grabbed all this, you would end up with this number. But here it's inverted. So why the mess, if you will? Well, the documentation talks about programming a fuse. And programming a fuse is not, as one might expect, putting a 1 in there. It's putting a 0 in there. Again, remember. That's why, and if you are online and if you're getting advice from somebody or seeing things, reading about it, you're going to have situations where people are saying program the fuse such and such. That's setting a 0 in it. Hence, this kind of intermediate, this whole area is talking about the same way you would find in the data sheet. The same kind of flag names, the groupings, everything is like that. And including the whole, you've checked the things you want to program, and program is actually setting them to 0. Hence that. From our point of view, outside of that, we don't need to. This is where we work. This is where we change we define what configuration do we want. And then we grab these numbers and we use them with the other app. And I'll show that in a second. So, okay, let's do something so that I can show you that. First, this is factory default. So I'll quickly tell you what this is. This is running with internal oscillator of 8 MHz. and then it's dividing that by 8. Notice that this would divide any oscillator, outside, external, whatever. It would divide that clock by 8 and then feed the resulting clock to the microcontroller. So that's the clock the microcontroller is going to be run at. In this case, 8 divided by 8, 1 megahertz. Right? So the first thing I'm going to do is I'm going to take this out. It's going to run full speed. Now the next thing I'm going to do is I'm going to set this to use an external clock. A clock is a fully formed digital signal that's a clock. It can be used to clock a digital signal. So it has 50-50 duty cycle, the appropriate logical levels of high and low, steady, fixed, ideally at least stable frequency, and square wave, as I said. So that's what a clock is. And this external clock basically says something's out there is going to generate me a clock. I don't care what. It's just gonna generate me a clock. And I take the clock in and I provide this to the microcontroller operating core. So that's what it is. I'm going to choose this option out of the 3, and later on I'm going to come back and explain what I mean. Right, so this has changed. What has happened? Well, this has changed, as has this. And you can see it because default is that and this is something else. So different fuses are going to be programmed. You can see that also here. So what we do with this? Well, copy and paste again. Only this time it's going to go in the reverse direction. Now, remember, you can see it also here, but remember, we didn't change other fuse configurations, so we don't need to copy and paste anything else. So what now? Well, right. That's it. This is the bit where you write the fuses. So, now we start a bit about the things that could go wrong. And this is why we chose as a configuration the external clock. Because, well, this is one way things can go wrong. So there are 3 different things that you have, kind of things that you have to pay attention to. The first one is about the oscillator clock configuration you chose. Now, these microcontrollers, other microcontrollers are not like this, but these ones are like this. If you set a clock configuration and you don't have the hardware, it won't run. That's kind of reasonable if you think about it. No clock, no running. The thing is, it will also not let you do anything at all with it, including reverse that clock configuration. I'll demonstrate by physically taking out the line that's coming from an external oscillator I have here. And now, yeah, it doesn't work anymore. And if I tried and reverted it to the default by, setting it there and just writing it, yeah, it gives me an error. It says device signature is not right. So, what's going on? Well, without the clock configuration, the hardware for the clock configuration I said it's going to be running with, it can't be programmed anymore. It won't properly respond to ISP programming. And that's it. Why is this a problem? Well, if you make a mistake, you're stuck. You can fix it once you get the hardware. So if you told the thing you're going to have an external crystal, well, you don't have the crystal, that's it. You can't do anything further with it. You can't program it, you can't run anything in it, you can't do anything with it. But if you get yourself a crystal and the 2 load capacitors and you install them in the right place, then you can go back. And I'll demonstrate here by simply restoring the line that brings the clock signal to the microcontroller. And yeah, see, now it's back on again. So that's problem number 1. Well, possible problem. So beware of that one. This number 2 is even more entertaining. So this is the lock bit. You will notice that the lock bit has its own series of buttons. You will notice it's empty. These 3 are all done together. These 3 are fuses. The lock bit is also fuses. Yet it's separate. Why? Well, lock bits lock. And they can lock reads from part of it, or reads from everything, or writes from part of it, and writes from everything. It really is like if you put a value here, something's going to get locked. And once locked, that's it. So it's very easy to make a microcontroller not usable anymore, right? Brick it in the speaking, terms for this. So you shouldn't actually be doing any lock bit configuration unless you really, really, really know what you're doing and you actually need it. So how do you get to really, really know what you're doing? Well, read the datasheet and really understand what's in there, right? When would you need it? Well, typically it's the kind of situation where, for example, you've made a product, you're going to ship that product, and you don't want people downstream to hack it or download the program you've been working on so long and make a competing product by just copying your code. Your binary in a sense, because it's going to be in Flash, but it's going to be the same. If they copy it from here and they write it to another chip from the same kind, it's just going to work there. So yeah, that's why you might want to lock it. It's for that kind of situations. If you're planning on carry on using this microcontroller, doesn't actually make sense to lock yourself out of using it further to its fullest. So yeah, that's potential problem number 2, lock bits. And that's why, because they're such a potentially big problem, that's why they have separate buttons, is so that you don't have some value here for some reason, you made a mistake and you go and write this thing in and yeah, you just wrote the lock bit. That would have been a problem. So no, you can't. You need to do lock bits specifically, and this application is trying to help you also in that situation. And in other ways of writing fuses, you will also see that often that pattern, that the thing is forces you to explicitly say, I want to burn a lock fuse, right? So that's it. Last one. Okay, here it's easy to spot. You can see the asterisks here, right? And if you go here, this is a high fuse, so it's in the high fuse section. You can also see the asterisks here. So what do they mean? Well, they mean that these things can cause you problems. How can it cause you problems? Well, debug wire is mostly because certain pins are not going to be working as you would expect it anymore if you enable this. Reset disabling and disabling of serial programming, that's more of a problem. If you disable reset by checking this, then you enable that pin to become an I/O pin. So it's not a reset pin anymore. If you bring a low to it, it doesn't really do anything. Well, you can read that low from your I/O pin, but it won't reset the microcontroller. So, what's the problem here? Well, how do you program it? If you're using ISP programming, remember, one of the wires is reset. It really does need to reset it as part of programming it. So if you don't have reset, it won't work. If you're using Arduino style programming with a bootloader, well, there are 2 ways to make the bootloader pop up. You either power down and power up the microcontroller, or you reset it. So in the Arduino boards, that's what happens. There's a reset. So there's a signal coming in via USB which causes temporarily the reset to be brought low, and then it comes up again. And then the Arduino IDE will start uploading the program by sending the appropriate commands to the bootloader, which, well, just after reset, it will be there listening for a couple of seconds. It gets the commands and it does its thing. If you don't have that, then you have to power it down and power it up. So you have to do it by hand. And to do it by hand and still be able to program it via serial, it can't be everything coming via USB. You can't just have USB there and have USB to provide power and also the serial comms, because how do you take power off whilst leaving the serial communications on so that the thing does go through? So you're trying to get your Arduino IDE to start programming it. You're trying to unpower the thing and power it back on again, and you want the Arduino IDE to keep on its cycle and sort of hit that small window where you've just powered it up and then the Arduino IDE is just about to start sending commands and it all works. Now, if everything is on USB, then when you unplug USB to unplug power, you also unplug the communications. So the serial connection goes down, so the whole thing fails. So you have to have them separate. You have to have a USB to serial adapter, separate one, and then you have to have power separate from that, so that you can leave the serial USB serial connection on, but take power off and then bring power back on. So yeah, it's messy. And you have to try and hit that small window of a few seconds, like literally 2 or 3. And that's not reliable now, is it? So yeah, this is why you wouldn't want to do this unless you really needed that pin. And even then, well, it's probably like the last thing you would do on all of this. Serial program downloading enabled. So it starts enabled. Remember, this is the factory defaults. It's still here, D9, D9. So, what's this? Well, ISP, also known as ICSP, stands for In-Circuit Serial Programming. So that's what this is. And check this, you don't have ISP programming. You still have a bootloader. If you have a bootloader in there, before you want to check, and then you want to check this and burn the fuses. If you have a bootloader already uploaded, then you do have bootload programming if the bootloader does that. So that keeps on working. That's an effect because that's just code that just happens to be there, and it's configured in a certain way that it's capable of uploading applications into the rest of the memory. If you don't, then yeah, you're stuck. You can't really do anything with it anymore. And if you do have a bootloader and you want to update it, no, you can't anymore, right? You don't have ISP programming. Same thing, you want to update the fuses. You're now going to use a crystal instead of internal oscillator. Yeah, tough luck now, isn't it? So yeah, that's the problem. There is a workaround, which is using something called high voltage programming. However, that thing is, well, people usually use ISP programming, so there's not that many options in terms of high voltage programmers. So getting your hands in one of those is going to be complicated. It's not just make your own thing by uploading something into an Arduino Uno and poof, there you go, works. No, that doesn't, well, you can't do it with a high voltage programmer. So yeah, beware with those 3 there. So yeah, that's basically it. So on to the last part. How do we do the configuration of fuses that you don't? Which fuses are going to be configured? Well, the first one we did already, actually. We've done the external clock. This is something you cannot do from the Arduino IDE with a miniCore. It's not there. The only externals that are there is using a crystal. And remember, a crystal is a component of an oscillator. So by configuring it to run with a crystal, you can see here there's configurations for it that's separate. By configuring it to run with a crystal, we're really just configuring the microcontroller to activate appropriately its internals, which are going to form the other side of the oscillator, which then works together with the crystal and the load capacitors to form an oscillator. However, an external clock is an entire separate whatever that's generating a clock. Now, a moment ago I showed you there were 3 options here and I didn't talk about it. So I'm going to quickly say what does this mean? Well, this part should be read as startup time after power down or reset. So this is the time that it takes to start up after you come out of a power down, meaning you power up, or come out of a reset. So the end of reset condition. And you can see here, there's a few clock cycles in there that you can't get away from them. But then there's a possibility of additional wait times. Why is that? Well, clocks come from oscillators. Something somewhere is going to be oscillating. There's no escaping it. And the real world oscillators don't start perfect. They start badly, right? What comes out of an oscillator when it's starting, it's generally garbage. It's not a proper clock signal. It might have missing cycles. It will have the wrong frequency almost for certain. It takes a while until the oscillator stabilizes. And the way oscillators are designed is they're going to stabilize at a certain frequency. They're going to stabilize around that frequency. The better the oscillator, the better, the closest it's going to be, and the steadier it's going to be over there. So crystal is much better than an internal oscillator. But that's the point. Once they stabilize, then it's fine. Then the signal is appropriate to pass on to the microcontroller's operating core as the clock. And the thing's gonna run from it. So here, this one with just no extra waiting time, this is only really useful if you have, in this case actually, the external clock can be useful if you have the clock already running somewhere else and then you power up or bring out from reset your microcontroller because, you know, the oscillator out there somewhere, it's already stabilized. So yeah, instantly you can go as fast as possible, go. That's it. The second one, this is useful for crystal oscillators, right? So maybe your external oscillator is crystal oscillator. Also here you can see there's those options over there. So crystal oscillators, especially the high speed ones, the lower speed ones in the kilohertz range, maybe not so much, but the megahertz ones tend to be ready within this point. But there's also this one. This is the safe option. This is, well, if it's not ready by this point, it's probably there's bigger problems in there, it's never gonna work. This is the, yeah, just in case I don't want to look at data sheets and whatever, I'm gonna go with this. Which is why when I was doing this, I just went with this one. This one's gonna work for sure. Why might you want this one? Because, you know, this is just a wait on startup. So 65 milliseconds is not really that much for a human. If a human is looking at it and I just powered it up, I'm not going to notice the difference. Yeah, but sleep mode, also some sleep modes will stop the clock and then start it up. So if you need the thing, if the thing is actually connected to some kind of machine type thing and comms are coming in, for example, or something like that, then it might make sense to get it up as fast as possible. Of course, if you're that urgently waiting for comms, maybe you just should use a sleep mode that doesn't stop the clock. But that's a different story. But here I'm just using the 65 milliseconds in general, and you can see here down here the internal oscillator, the factory default, also uses the 65 milliseconds. Also because it's an internal oscillator, so it's less likely it's going to be ready at 4.1. But it is the kind of, you know, it's the easy option and it works, and it's not, there's rarely reason not to go with this. So there you go. And now this is what's in there already. So what's the other fuse configuration options that might make sense? Well, clock output. You can get this microcontroller to output its clock. Now you might be wondering what's the point, right? Well, some microcontrollers and some digital circuits in general require an external clock. You don't have other options. You have to use an external clock. Some microcontrollers from this AVR range actually only have two options, which is the internal oscillator or the external clock. So if you want to run certain things like fast serial from it, the internal oscillator, although quite better than the ATmega328Ps, might not be good enough. So at that point you need an external clock. Where from, right? And more so for the other digital circuits. So I'm going to give you a concrete example. Say you have a waveform generator, right? Many waveform generators require an external clock. 12 megahertz, right? You need a 12 megahertz clock. So you might have to get like a quartz oscillator, which is an entire oscillating circuit with a quartz crystal inside, but it's a self-contained circuit in a box. It takes power, it gives you a clock. That's basically it. So you'd have to have a 12 megahertz one. That's kind of biggish, and that's kind of, well, it's 4 or 5 more times the price of a crystal. If you have a microcontroller right next to it that is capable of running a crystal, why are you going with the expensive option? In addition to this, because this also needs to run. So this is the kind of situation where it makes sense. You need 12 megahertz. Okay, I'm just going to make this thing run with 12 megahertz. And that's basically here. I'm going to use an external crystal oscillator, although it's not really, the oscillator is with a crystal, so it's an oscillator with an external crystal. That's how you best read it. And it's for a range of frequencies. So this doesn't tell you the frequency of the crystal, it just tells you the kind of crystal it is so that it adjusts the internal circuitry appropriately for it. So at 12 megahertz is this one. So there you go. Then I would install the 12 megahertz externally and the load capacitors wired to this thing, and then this thing is running at 12 megahertz. Lo and behold, if you do this, not only is it running at 12 megahertz, it's outputting a perfect clock signal, and it's going to be a strong clock signal. It's not going to be a pass-through or whatever. It's going to be properly driven with the right digital levels, enough current, steady frequency, the qualities that we would want if you're doing the inverse and you're saying this guy's going to run from external clock. That other option is going to produce that kind of external clock, and lo and behold, you can wire it to the waveform generator and poof, problem solved. There you go. That's why you would want to have something like this. So, to summon it, you can use AVR DUDES on top of AVR DUD, and you can get your AVR DUD with already the Arduino miniCore, so you don't need to worry if you have that already. And you use some kind of AVR fuse calculator, not necessarily this one, but this one is fine, to do the maths, to let you configure it in a nice way, rather than having to muck about with bits and bytes. And remember, block bits, yeah, don't do the clock configuration if you don't have the hardware for it, and beware of the ones with asterisks. So yeah, that's it.